The scenario we're going to be considering is a collision between two cars we will refer to as car A and car B. So car B is stationary at a red traffic light. Car A, on the other hand, is traveling with an initial velocity v0 down a hill. So both cars are on a hill, and car A is traveling initially with a speed of v0. So this is just when car A, the driver of car A, realizes that he is on a collision course with car B. So the driver then decides to step on the brakes, at which point car A begins to slide down this hill towards car B. So the stepping on the brakes obviously doesn't work because car A still ends up slamming into car B. So what we are to find is the velocity at which car A slams into car B. And what we're provided is that the distance between car A and car B at the instant that the driver of car A steps on the brake is 24 meters. We're also provided the angle of inclination of the hill that car A and car B are on. So theta is equal to 12 degrees. And we're also giving the initial speed at which car A was traveling just when the driver decided to slam on the brakes. So V0 is equal to 18 meters per second. So our goal in this video is to find the speed at which car A collides with car B, given that the coefficient of kinetic friction between the road and the tires of car A is 0.60. Okay, so that's the first part of our of what we are to do for this problem. And the second part, part B, is to find the speed at which car A collides with car B, given that mu, the coefficient of kinetic friction, this time is 0.10. Okay, so in other words, we are to find the final velocity of car A once it strikes the back of car B. So the way we're going to do this is very simple. Let's see here. Actually, let's keep this picture so that we can refer to it. So the way we're going to solve this problem is by considering that just when the driver of car A steps on the brake, right, there is no gas being applied to the car. And so, in a sense, the car is sliding under the action of only two forces, okay? So I'm sure you can guess what those two forces are. But those two forces are going to be the frictional force from the road between car A and its tires, and the frictional force is going to be directed to the left. So you'll have the kinetic frictional force directed to the left. We'll write it as F sub K. Now, at the same time, remember, there's no gas being applied to the car. So that means the car is, in a sense, falling, right, downwards, down the hill. And the force that's allowing it to keep on moving down the hill is going to be its weight force, the weight of the car. So the weight of the car is going to insist on driving the car forward, while the kinetic frictional force is going to act against the motion of the car. So for the kinetic frictional force, for the weight of the car, we can write it as W sub X. Okay, so we are considering the weight of the car to be pushing the car in that direction, whereas the kinetic frictional force is trying to slow down the car in this direction. Okay. Now, I'm not going to derive this, but the weight component of the car going down the hill is going to be equal to minus mg times sine of theta. Okay, so if you're familiar with dealing with decomposing the weight of object on an inclined plane, then you should know that Wx is always equal to the magnitude of the weight of the car. The component of the weight of the car is mg sine theta. I simply put minus attached to this expression because I'm considering the leftwards direction to be the negative direction and the rightwards direction this way to be the positive direction. Okay, so Wx equals minus mg sine theta. Now, as for F sub k, we need to write an expression for that. So F sub k, the kinetic frictional force, is going to be mu times mg cosine of theta. Okay, so remember the frictional force. The formula for frictional force is F is equal to mu times the normal. Okay, so that's going to be the normal force acting on the object. Okay, so in this case, we're talking about kinetic frictional force. So F sub k is equal to mu, which is the coefficient of kinetic friction, times the normal force. What is this normal force? Okay, the normal force is going to be the component of the weight of the car that is perpendicular to this plane. So, for example, suppose I drew the weight of the car. Let me get a ruler here. So suppose I drew the weight of the car going directly downwards like this, and I'll call it mg. Okay, so the normal, I can make a perpendicular line to the incline of the plane. Okay, so this perpendicular line will have the normal force acting along that line, right? We can maybe even write it like this. Okay, so if you notice, there's an angle here, and this angle theta is the same as this angle theta by geometry. So if you can see here, we have a sort of right triangle over here, which means mg times the cosine of this theta is the normal force, which is what I've written over here, mg cosine of theta. By the same analysis, mg times sine of theta is going to give you the weight component of this car. So these two forces are derived simply from the weight of this car. Okay, so let's clear that out a bit so that we can get back to the picture. Right, so since the car is sliding, there's going to be, since the car is sliding on down the hill, there's going to be a net force acting on this car because you have two forces that are acting on this car. The net force acting on this car, we'll write it as F sub net, is going to be the sum of these two forces. So that's going to be F sub k plus Wx. Okay, and that's going to simply be mu times mg cosine of theta minus the value of Wx. So that's going to be minus mg sine of theta. Okay, so this is the net force acting on this car A. So by Newton's second law, this net force is equal to the mass of car A multiplied by its acceleration down the hill. So we can write that the mass of car A times acceleration is equal to mu times mg cosine of theta minus mg sine of theta. Okay, and which means we can solve for A. So A, I should probably, I'll erase the subscript A because we already have M here and we know we're talking about car A. So we can get rid of this and we can solve for A. Okay, so that means that A is equal to mg cosine, mg times mu cosine of theta minus sine of theta. Okay, so A, the acceleration down the ramp of car A, is equal to mg times mu cosine theta minus sine of theta. Okay. Now that we have an expression for A, we need to find the final velocity at which the car strikes car B, at which car A strikes car B. Now, if you remember some of your kinematics equations, right, that will be really helpful at this point, because with this information, you can use the formula 2AD is equal to V sub F squared minus V sub 0 squared, okay, which means you can solve for V sub F. V sub F is then equal to 2AD plus V0 squared square rooted, okay? And we know what A is, right? We've gotten an expression for A. So we can therefore write that V sub F is equal to the square root, this is going to be a big square root, of 2 times, let's see here, so I don't miss anything. Oh, there we go. The m's cancel out, so we don't need this m here. So neglect the m. So A equals g times mu cosine theta minus sine theta. So V sub f is then just 2 times g times d, right? And of course, we have to be aware that d is the distance between the two cars, right? Our concern is with car A, so we use the distance that car A travels, which is just d, 24 meters. So the final velocity is the square root of 2 times g times d times mu cosine of theta minus sine of theta plus v0 squared, okay? And at this point, what we can do is we can plug in the values of mu in order to solve for part A and part B. We already know v0, we know theta, and we know g. So I think it goes without saying that at this point, the entire problem is solved. Simply plug in the values, and let's see, we had to solve for part A, mu equals 0.60, and part B, mu equals 0.10. Okay, so it goes without saying that since we have pretty much all of these values, we can simply plug them in and then calculate the final velocity for these two different values of mu.